Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we had a brief introduction about electric drives and what are the advantages of electric drives. And in this lecture, we will start with the discussion on dynamics of electric drives. Now, what we have a motor which is mechanically coupled with a load, and we will see the relationship between the speed and the torque. So, what we have here, we have a motor and this motor is coupled to a load. This is a load and here is a mechanical coupling which is coupling the motor with a load. And the motor has a torque that is equal to T, which is in one direction, and the load is opposing the motion. The load torque is designated as TL, it is in the opposite direction. And we have a speed here, the speed is in this direction, the motor is trying to drive the load and the speed and the torque here are in the same direction. Now, we can write down a mechanical equation. The total moment of inertia is J. So, this is a rotational system. The mass is rotating and the motor is driving the load. Now, what is the dynamic equation here? The dynamic equation is that the motor torque is T and the load torque is TL, that is equal to the rate of change of angular momentum d by dt of J is the moment of inertia, and omega m is the speed of the system, speed of the motor load combination, and J into omega m is the angular momentum. So, the differential torque T minus TL is the rate of change of angular momentum. Now, if we expand this derivative, we will have two terms like this, J d omega m by dt plus omega m dj by dt, if we difference in parts. And usually the inertia is constant, inertia does not change with time. So, we can assume that this quantity is 0, this quantity is 0. So, when we assume that there is no rate of change of inertia, there is no change of inertia, the inertia dj by dt can be equal to 0. So, what we finally get here is T minus TL is J d omega m by dt. So, we can also write down here that the motor torque, this is the motor torque, is equal to J d omega m by dt plus TL. Now, what is J? J is called the moment of inertia. What is d omega m by dt? This is called the angular acceleration, angular acceleration. Omega m is the speed, the derivative of that is the acceleration, angular acceleration, d omega m by dt is angular acceleration. And what is TL? TL is the load torque. So, this is an important equation which is valid in the steady state as well as in the transient condition. Now, we will in the steady state what happens in steady state, usually omega m is constant, speed is constant. Now, if speed is constant, we can say that T is equal to T L, because d omega m by dt is equal to 0. There is no acceleration in the steady state. When the motor has reached a steady speed, we call steady state. In the steady state, there is no angular acceleration. So, the inertial torque j d omega by dt, that is equal to 0. So, in the steady state, motor torque is counterbalanced by the load torque. So, the speed is constant, motor and the load torque are opposing each other. Now, we will discuss about the speed torque convention. And multi-quadrant operation of electric drives. Now, we now understand that when we talk about electric drives, we have two variables, one is speed, other is torque, two mechanical variables. So, we have to control the speed of the motor, we have to control the torque of the motor. So, these are the output of the motor and these variables are very important to us. So, we have to control the torque, we have to control the speed. Now, when we plot in an xy plane, we have two variables. So, we can plot this in an xy plane. The speed is usually taken in the y axis and torque is taken in the x axis. This is the convention. So, when we draw the speed torque characteristic, speed is in the y axis and torque is in the x axis. So, this is how we draw the speed torque characteristic. So, we have omega m is the mechanical speed and T is the torque. So, this is our torque in the x axis and speed is in the y axis. And in SI system, we represent speed in radian per second. Speed is usually radian per second and torque in SI unit is represented in Newton meter. So, this is in Newton meter. So, this is the origin here. So, this is quadrant 1, we have xy plane, this is the quadrant 2, the second quadrant, we have quadrant 3 and we have quadrant 4. So, we have 4 quadrants. So, in the first quadrant, the speed is positive, torque is also positive. So, when we talk about power, the power is a product of speed and torque, that also positive. So, we call the first quadrant operation as forward motoring. This is called forward motoring. In the second quadrant, what happens? The speed is positive, but the torque has become negative, because the second quadrant is in the left hand side here. So, the torque is negative. So, when the torque is negative, power, which is the product of speed and torque, that is negative. And we call the second quadrant as forward braking, because the power is negative. So, power flow is from the motor to the source. So, the motor is behaving as a generator now. So, that is why we call the forward braking, the motor is braking. So, the torque is reversed here. So, this is called forward braking in the second quadrant. So, in the third quadrant, we see that the speed is negative, torque is also negative. So, both the variables are negative. Power which is the product of speed and torque, this is positive. So, the power flow is positive from the source to the motor, and this is called reverse motoring. The motor is motoring, but the speed is negative. When the speed is negative, we call it to be reverse motoring. In the fourth quadrant, we see that what is the speed here? The speed has reversed. Speed is negative. What about the torque? The torque is positive here. The speed is negative, but the torque is positive. So, what about the power here? Power is a product of speed and torque. This is negative. So, when the power is negative, it is braking, and since the speed is negative here, we call this to be reverse braking. So, the fourth quadrant characteristic is reverse braking. The fourth quadrant is reverse braking. So, when we call it is braking, the braking means power is negative, the motor is behaving as a generator. When we call motoring, power is positive. So, power flow is from the electric source to the motor. Now, let us see an example of this multi quadrant operation. We have four different quadrants. Quadrant 1 is forward motoring, quadrant 2 is forward braking, quadrant 3 is reverse motoring, and quadrant 4 is reverse braking. Now, let us see a practical example of this 4 quadrant operation. Now, we take a hoist, or in simple word, this is a lift, either carrying main or material. Now, when we talk about a hoist, we will try to understand the operation of the hoist in 4 different quadrants. So, this is our origin, and we have speed in the y axis here, torque is in the x axis. So, we have a pulley mechanism here, and there is a hoist which is loaded, and always we have a counterweight. This is a counterweight. So, this is a cage of the hoist which is loaded, and this is the counterweight. And the motor is coupled with this pulley. In the first quadrant, we have the quadrant 1 here, this is the first quadrant. In the first quadrant, we are lifting the cage, lifting the loaded cage. So, the motor has to rotate in the anti-clockwise direction, this is the speed of the motor. And our condition here is this, that the weight of the loaded cage is greater than the weight of the counterweight, weight of the counterweight. The weight of the loaded cage is greater than the weight of the counterweight. So, in this case the load torque is below, down below. So, this is the load torque. So, the load torque is trying to drive it in the clockwise direction. The motor torque and the load torque always oppose each other. If this is the motor torque, load torque opposes the motor torque. So, the motor torque will be in the opposite direction. Here is this, that is T. So, T is the motor torque, omega m is the speed, and the load torque, which is T L, is opposing the motor torque. So, here the T and omega m are in the same direction. So, T is positive, omega m is positive. So, the power is positive. So, this is forward motoring. We have already discussed about this. This is forward motoring. Now, in the second quadrant, we have this pulley mechanism to which the motor is fixed. The cage is now unloaded, there is no material in the cage, the counterweight is here. So, our condition here is that weight of the empty cage, the cage is now empty, is less than the weight of the counterweight. So, here is the empty cage. So, this is an empty cage here. And this is our counterweight. And the speed is again in the anticlockwise direction. We are trying to lift the the empty cage. So, this has to go like this, the motion is like this here. So, this is omega m, but the load torque is in this direction and the motor torque will oppose the load torque. So, this is our motor torque T. So, in this case omega m is still positive, we are lifting the cage, but the cage is now empty, but the torque has reversed and hence the power is negative, power has reversed. So, this we call to be forward braking. Okay. So, we have already seen in first quadrant it is forward motoring, in the second quadrant we have the forward braking. Now, let us come to third quadrant. In the third quadrant, this is quadrant number 3, we have this mechanism, the pulley mechanism here, and what we are trying to do here, we are trying to lower the cage. This is a counterweight here, we have the pulley, in this case the cage is empty. So, we are lowering an empty cage, we are lowering an empty cage. So, in this case what we have to do here, the speed is in the clockwise direction, this is in this case, and the counterweight is having more weight than the empty cage. So, the torque is in the anticlockwise direction T L, the motor torque will oppose the load torque. So, the motor torque is in this direction. So, this is the counterweight. So, in the third quadrant what we have, speed is negative here, the speed is reversed, we have to load this cage now, the torque is also negative and hence the power is positive, the product of torque and speed is the power, that is positive. So, this is called reverse motoring. Motoring in the reverse direction. Let us see the fourth quadrant. In the fourth quadrant we have this pulley, and what we are trying to do here, we are lowering a loaded cage here. The cage is now not empty, but it is now loaded, and this is a counterweight. So, this is the cage which is loaded and this is the counterweight. So, when the cage is loaded, we are trying to lower it, the speed is in the clockwise direction which is negative, the torque is in this direction because the cage, the loaded cage has got more weight. So, we have this is the direction of the load torque. The motor torque has to oppose the load torque. So, this is our motor torque. So, here what we find here that the speed is negative, but the torque is now positive. But since the speed is now reversed, the speed is negative, the power is negative, and this is called reverse braking. So, these are the 4 different quadrant, and when a drive is capable of operating in all 4 different quadrants, quadrant 1, quadrant 2, quadrant 3 and quadrant 4, we call that drive to be a 4 quadrant drive, and we call this operation as a 4 quadrant operation. So, this we call as a 4 quadrant operation. So, the 4 quadrant operation means the drive should be able to operate as forward motoring, in forward braking, reverse motoring and reverse braking in all 4 quadrant of the speed torque plane. So, we will now see suppose the motor and the load are not directly coupled, they are coupled by means of some gears or by means of some sort of pulley. So, how do we see the combined equivalent inertia and torque of the entire combination seen by the motor? So, we will be discussing about the equivalent drive parameters. Equivalent drive parameters. Now, what we have here, we have a motor which is directly coupled to a load. This is a load and this we call that this is a load number 0, and the motor is directly coupled with this load. So, this load is offering a torque of TL 0. The motor, the speed is in this direction omega m, and the inertia of this combined system is J naught. The moment of inertia is J naught here. Now, this motor and load combination is coupled to another system using mechanical gear. This is a gear, and this is driving a load. So, this is another load, we call it to be load 0 and we call this to be load 1. And when we have these gears, the gears will have some sort of some teeth mechanism. Okay. The motor side gear has a teeth of number of teeth is n, and the load side gear has a number of teeth is n1 here. And this is the speed which is omega m, the motor side speed, and the load is being driven by the speed which is omega m1, because the gear ratio is not 1, that is why the load speed is different, the load 1 speed is different from the motor speed which is omega m1, and the inertia of load 1 is J1, and the torque which is being offered by load 1 is a load torque which is TL1. Now, when this system is coupled to the motor, we have to see what is the equivalent inertia seen by the motor and what is the equivalent torque seen by the motor. Now, let us first talk about the gear ratio. The gear ratio here is the number of teeth of the motor side by the number of teeth of the load 1 side, that is n by n1. Now, if we take the ratio omega m1 by omega m, this is equal to n by n1. The speed of a system is inversely proportional to the number of teeth. If the number of teeth is more, speed will be less. If the number of teeth is less, speed of that particular system is more. So, the ratio of the speed is equal to inverse of the number of teeth. So, omega m1 by omega m is n by n1, and that we call as a1. Now, we will try to see the equivalent inertia of the entire system. So, what is the equivalent inertia? We have to see the kinetic energy of the entire system. When the motor is rotating, the load is rotating, they are possessing some kinetic energy. So, the equivalent kinetic energy is half j omega m square. The kinetic energy is expressed as half of moment of inertia into the square of the speed. That is equal to kinetic energy of the 0th part, that is half j naught omega m square, plus the kinetic energy of the second part, which is half j 1 into omega m 1 square. So, this is the equation which gives the kinetic energy of the entire system. Now, if we want to find out the equivalent kinetic energy moment of inertia j, from this equation we can take this omega m square to the right hand side, that is equal to j naught into omega m square by omega m square plus j 1 omega m 1 square by omega m square. That is equal to j naught plus j 1 into omega m 1 by omega m is a 1. So, this is a 1 square. So, j is equal to the total inertia seen by the motor is equal to j naught plus j 1 into a 1 square. Similarly, let us see the power seen by the motor. So, if you see the power seen by the motor, so the power seen by the motor is T L into omega m, that is equal to, we have two different loads. Load 0 is directly coupled, load 0 power is T L naught into omega m naught, plus load 1 power is T L 1 into omega n 1. Now, whenever we have a mechanical gear, the mechanical gear has got some efficiency. Efficiency is not always 100%. So, we say that eta is the efficiency of the gear, efficiency of the gear. So, if eta is the efficiency or eta 1 is the efficiency of the gear, so this is divided by eta 1, because the power which is seen by the motor is higher than the power which is running the load 1. So, this is T L 1 into omega m 1 by eta 1. So, again we can take this omega m to the right hand side, T L is equal to T L naught into omega m naught by omega m. Omega m naught is same as omega m. So, this is in this case same as omega m here, plus T L 1 by eta 1 into omega m 1 by omega m. We can simplify this, this is equal to T L naught plus T L 1 by eta 1 into A 1. So, this is the equivalent load torque seen by the motor. Now, if we have multiple couplings attached to a motor, and coupling has got various gear ratio like A1, A2, A3, A4, and each coupling has got the efficiency eta 1, eta 2, eta 3, eta 4. we can derive a general equation, or we can write the equivalent inertia and the equivalent torque by means of a general equation. The general equation is equivalent inertia J is equal to J naught plus A1 square J1 plus A2 square J2 plus so on. A1, A2 etc. are the gear ratios, and similarly the equivalent load torque is equal to TL naught plus A1 TL1 by eta 1 is the efficiency of gear 1, A2 into TL2 by eta 2 is the efficiency of gear 2, and so on. So, we have already seen here how we can derive the equivalent moment of inertia and equivalent load torque when the motors is coupled with a load through a gear. So, we stop here for today's lecture. We will continue in the next lecture.